Hello, I'm Abhilash. I'm going to present our work on enhancing tabular reasoning with pattern exploiting training. This work is jointly done with Vivek Gupta. Natural language inference is the problem of categorizing a hypothesis into entailment or contradiction or neutral based on the given premise. Understanding semi-structured data like tables requires not only comprehending the meaning of the text statements but also the implicit relations between them. Here is an example from the input types dataset. Now in the tabular NLI task, we need to classify a hypothesis into true, false, or undetermined from the given tabular premise. For the hypothesis, Breakfast in America is a pop album with a duration less than 50 minutes. Model first need to find the relevant rows to classify this hypothesis. The relevant rows in this example are the length and the genre. The model needs to get this relevant rows and performing reasoning over them, which is like comparing 4 to 6 minutes with 50 minutes and if the pop album exists in the values of the row genre. And similarly, in another example, the album was produced by one person. The model first need to find the relevant row, which is the producer, then need to count the number of producers in that row. Not only arithmetic reasoning, model also require other reasoning skills such as in the example Breakfast in America was released towards the end of 1970. After finding the relevant row released, model needs to compare the end of 1979 with the 29th March 1979. Uh, Model also need to have the common sense knowledge that end of the 1979 is not 29th March 1979. So the model now needs to predict the statement as a contradiction. Now, for the example, Breakfast in America is recorded in California. Now the relevant row is the row with the key studio, not with the key recorded. Now the model needs to extract the relevant row and also need to compare that the village recorder is in LA. That means that LA is short for Los Angeles, and the model should needs to know that and also know that the Los Angeles is in California, which requires the model to have the factual knowledge about the Los Angeles and California. Recent methods based on pre-trained language models have exhibited superior performance over tabular tasks such as tabular NLI, despite showing inherent problems with reasoning over the tabular data. In this work, we want to investigate if the current models reason with existing knowledge, that is, can extract the right knowledge and correctly infer from that extracted knowledge, and can we enhance the tabular reasoning? Is it possible to improve the reasoning by incorporating the knowledge? Uh, and due to the existing biases in the training data with the hypothesis having annotation artifacts, often models trained on such data lack generalizability and robustness. We also want to investigate that how do we ensure robustness? Does our proposed model uh, is robust to spurious correlations? Language models, while learning the linguistic knowledge, they also store the factual and relational knowledge present in the training data. As many of the models are trained on huge corpuses like Wikipedia, there is a high chance that it might remember something from it. The tables used in the work are also derived from Wikipedia, so it is very important to assess the effect of retraining on tabular reasoning and determine if the models can infer from that knowledge. We evaluate knowledge using fill-in-the-blank style closed statements, both in presence and absence of the premise. In this example, duration of breakfast in America is 46 minutes. Now we create a prompt which captures the factual information. Here, breakfast in America and 46 are the factual information present in this hypothesis, and similarly create another prompt which is Breakfast in America was masked towards the end of 1979. Here, released is the relational information present in the statement. In this way, we were able to evaluate the both factual and relational knowledge of the model. Prompts for knowledge evaluation are constructed based on the sparser speech. We mask proper nouns and numbers to evaluate the factual knowledge, and we mask verbs to evaluate the relational knowledge. These prompts are generated using the hypotheses from the sets which have similar distribution as the training data. To check the effect of the premise, the input for querying the model is modified as premise plus prompt, which is the model is queried in present of the premise. We also use tools like WordNet to ensure the proper evaluation of the knowledge. Here we reformulate the tabular NLI task as the closed-style questions and perform gradient-based fine-tuning using a more supervised pattern exploiting training approach. The model is tasked to predict the masked word from the vocabulary, and the more supervision is achieved from the label token loss and by applying a label condition mask language modeling objective. For computing the label loss, the model computes each token's probability as a softmax normalized over all tokens, allowing the logics of all vocabulary tokens to impact each likelihood, similar to the regular mask language modeling objective. For label condition masking, inverting the query to the model to, in light of the answer, what is the appropriate constant from what is the appropriate label based on the input. The label condition mask language modeling is introduced by randomly masking out tokens and predicting the correct tokens if the label is true, and if the label is incorrect, model is forced to ignore the original token. The absence of comprehensiveness test sets hinders the robust model evaluation. Thus, evaluating models based only on the accuracy does not reflect their reliability and robustness. In a realistic scenario, the input text may contain typos, misspellings, negations that should not cause any changes in the model outcome. Applying automatic or human-controlled perturbations to textual inputs has been shown effective for evaluating robustness of NLP systems and investigating their vulnerabilities. We use a variety of character-level and word-level perturbations on hypotheses to replicate the circumstances in which the input is somewhat noisy or diverges from the training distribution, and we automatically relabel them based on simple logic. Here are the list of the perturbations that are used for evaluating the robustness of our model. These are some of the examples generated using various perturbations. While altering locations, cities are swapped with other cities only, and same goes with nationalities and countries. Names and locations are identified using an year, and they are swapped using a dictionary. There are challenges in generating the adversarial data. One is labels of the data might change when a perturbation is applied. For the perturbations like character and paraphrase, as there is no change in the meaning, there will be no change in the hypothesis. But for some other perturbations like location and numbers, there is a change in the label due to the perturbations applied. For example, breakfast in America is located in California. If you change the location from California to Texas, now the entailed statement will become a contradiction. Similarly, in other perturbation also, this happens. Our experiment uses a tabular inference dataset introduced by Gupta et al. Called InfoTabs. In addition to the conventional development and testset alpha-1, an adversarial testset alpha-2, which is lexically equivalent to alpha-1 but with minor changes in the hypothesis to flip, entail, and contradict label, and a zero-shot cross-domain testset alpha-3 containing large tables from other domains that are not in the training set are used for evaluation. We explore two ways to represent a table, which is one is table as a paragraph. Instead of using a universal template, the K of TRV, we use entity-specific templates based on the category of the tables and the entities to represent a table as a paragraph in a better way. We use distracting row removal, which prunes the table based on the similarity between the hypothesis and the table rows using alignment-based retrieval algorithm with fast text vectors. To answer the research question, can the language model reason with existing knowledge? Does our adaptive training approach enhances the model reasoning ability? Here are our results. In all the settings, with and without premise, our model outperformed knowledge input tabs in both factual and relational knowledge evaluation. Our approach performs almost as comparable to Robusta Large, and it is even outperforms it even in the entire settings. You can see here the Robusta plus classifier model, which is the model used in the knowledge input apps, which is far less than the model that we propose here, which is ADAPAD. With our approach, performance on relational knowledge evaluation is 2 times of that of knowledge input apps. We evaluated on contradiction hypothesis to assess if the model can rightly identify false claims despite having the correct entity types. Due to the false claims, performance is less on mix of entail plus contradiction hypothesis when compared to the only entail hypothesis. To answer another research question, can our approach of adaptive training benefit the model by incorporating knowledge for better reasoning on downstream tabular NLI tasks on input apps? Here are our results trained using our approach on input apps. Our adaptive approach improved over knowledge input tabs with all the table representations and using a pre-trained language model on a mixed dataset of ANLI, MNLI, SNLI, and fever NLI still improved the performance even further. We noticed that using the proof table representation only having top 8 rows outperforms every other representation of the table. It even outperforms the top 4 representation of the table in Alpha 2. And with using pre-trained language models, performances using better paragraph representation, which is without any pruning, and with pruning is almost comparable. And training a classifier on top of our adapted models also improves the performance, but it was only marginal. The average number of rows in the tables in testset alpha 3 is higher when compared to the number of rows in tables of alpha 1 and alpha 2. Because of this, pruning improved the performance a lot when compared to the approach without pruning. Overall, the pruning with top 8 rows improves the performance, especially in the class domain testset alpha 3. To answer our final research question, can language models trained on adaptive approach be more robust to spurious correlations? We trained our adapted model on input apps, then tested the model on our adversarial test sets. And here are our results. We see a maximum improvement of adapted in the test set negation, which has the counterfactual statement. And in the challenge test set with multiple perturbations, numbers, then paraphrase hypothesis, adapted-based models outperform a knowledge input as by 2 times. We observed that training a classifier after adapted performs with perform better when compared to the other models on the test sets with multiple perturbations. We also observed that using NLI pre-training the also helps to significantly improve the robustness. In many adversarial test sets involving multiple performations, all the models are performing poorly, even worse than random guessing. In the test sets where names are perturbed, even the NLI pre-training did not improve the performance. Performance was even worse when compared to the performance on Alpha 1 and Dev sets. While our model's performance on the challenging adversarial test is lower than the benchmarks on info tests, we don't know its reason. The created test sets may be challenging because they focus on the phenomena that existing models cannot capture, or it exploits the blind spots in the model's training set. In future, we want to improve and assess the reasons behind these results. The main takeaways from our work are: we introduced simple and effective prompts to evaluate knowledge, and we studied the effect of various table representations both on fine-tuning and prompt-based methods, and we also constructed challenging test sets to assess the model's robustness to names, numbers, location, and others. Thank you.